Welcome to this video on constraint optimization, and the type of constraint optimization we'll be doing is equality constraints. I'm going to take a look at the intuition for how we solve these types of problems first, then the theorem that we use, Lagrange Theorem, and what it is by definition. Then I'll give you a general approach to solving these types of questions following a step-by-step process. And then lastly, I'll finish the video by using that step-by-step process to solve a specific example. All right, let's get into the video. So constraint optimization, we're looking for maximizations of a objective function, but now we have a constraint. It's a bit unclear, but what that says is h of xy is equal to c. So in addition to maximizing the objective function, we need to satisfy this constraint here. And instead of finding turning points, we're now looking for a new concept, which is tangency between the level curve and the constraint. Okay, let's take a look at this through an example, give some intuition for what's going on. Let's say we're looking at demand and we're trying to maximize utility for our utility function u in terms of x and y. And our constraint here is that the money that you spend in the market, so px times x plus py times y, the amount of money that you spend must be less than or equal to your income. And x is greater or equal to 0, y is greater or equal to 0. And essentially what we're doing is we're maximizing utility subject to the constraint that you have actually spent the total money that you have, no more than that, and that you're buying positive, at least non-negative amounts of goods. Another way of looking at it is we could have our utility function is x to the half, y to the half, and our constraint is x plus y is equal to 10, just to give some numbers to this. And if we were to graph it, it would look something a little bit like this. And when you look at this graph here, we can plot in some indifference curves, which are curves that demonstrate all the points that achieve the same utility. And when we're maximizing our utility function, we're trying to push out these curves as far from the origin as we can go. The further we push them out in this direction, the larger utility value they represent. And the maximum in terms of this question is going to occur at the furthest curve from the origin that is still on our budget constraint. And that occurs at exactly this point where the budget line is tangent to the indifference curve here. So what's actually happening in this moment? Well, the gradient vector of f, or of u, in this case, utility function, is pointing perpendicular to this tangent, perpendicular to this budget line in this context here. And the idea is that the budget line and the slope of the indifference curve are parallel to each other. And if we can find when they're parallel, we have this tangency condition being met. And that's what we're looking for to solve these types of questions. So don't worry too much about that stuff. We can keep moving. Essentially, a summary of what I'm saying is that unconstrained optimizations, we're looking for turning points where the gradient vector is 0 and they look like this. Constraint optimization, we're looking for tangency where the gradient vector of the objective function is parallel to the gradient vector of the constraint function. That is referring to this one over here. And that looks something like this. Okay, why are we doing this? Well, in addition to the graphical representation, we can talk about it intuitively as to why logically it makes a lot of sense that this is going to occur the optimal solution. Imagine you had a scenario where grad f is equal to 3, 4 and grad h is equal to 1, 1. So what that is telling us is that at this supposed optimal solution, it's not, but we're looking at this as a potential. The derivatives of the objective function with respect to x and y is 3 and 4, and then the derivatives of your constraint function are equal to 1 and 1. So I think the objective function is pretty obvious. That means if you increase x by 1 unit, your objective function goes up by 3. If you increase y by 1 unit, your objective function goes up by 4. But what does this mean? Well, this here is referring to this constraint condition. And if this is equal to a constant and the derivatives are 1 and 1, that means that for it to remain equal to the constant, you would need to increase x by 1 unit only if you decrease y by 1 unit also. If you do that, then you'll get +1 -1, no change overall, and you will remain equal to a constant. That is the way that you can interpret this here. And so together, we now have the rate of change of increasing x or y for the objective function, and the rate of change of x and y on our constraint constant c. So why does this make no sense for being a solution when we're maximizing something? Well, we can just play around with the current answer, the current x, and by x, I'm talking about the vector of inputs. And here, we can hold constant c by increasing y by 1 and decreasing x by 1. So if y goes up by 1 and x goes down by 1, according to this, that will keep things constant. But the effect that that has on our gradient, on our objective function from our gradient vector, is that the objective function will go up by 4 and down by 3, which is a net change that's positive. Of course, I'm talking at an approximate level when I'm increasing it by a whole unit. This is instantaneous, but moving that direction is going to achieve things in the same way that I'm talking about. So going +1 to y, -1 to x will keep things constant in terms of the constraint, but will increase the objective function. And as a result, we've now improved our situation, and this new point is preferred to the old one. That means the old one cannot be optimal, cannot be the max. And that's exactly why we need to have a parallel relationship between these two vectors. In terms of the optimal solution, you need to be able to, you need to be unable to improve your situation by trading between x and y legitimately and then improving f. And if these are parallel to each other, like 10, 1, and then 110, then if you trade in a way that keeps things constant, the impact that has on the objective function is not going to change things at all. And that's the summary of what is written in text below. Okay, let's keep going. So, whilst generally this idea is a good one, when can this go wrong? So, trading between x and y along your constraint is good so long as it's possible. And if you run into the boundary of your problem, then you can't trade between x and y, and so you might not have tangency occur at the optimal solution. So an example for this would be if our indifference curves look like this and they're getting maximized by going in this direction, then the furthest out you can go is going to be here, which is on the corner of this budget constraint, but it's clearly not tangent. The tangency would occur like over here. That was a terrible line. The tangency would occur over here. This is not tangent, but it is the furthest out you can go while being constrained to the budget constraint. And yeah, this here is optimal and not tangent. So what's going on? Well, the quick answer is that it sits on the corner, and it's not so silly anymore for it to look like this if there's an extra constraint that says, oh, by the way, you can't increase y anymore. Well, in this case, you can't increase x anymore, which is what's going on here. Okay, so the quick answer is we need to check for boundaries as well, because they can sometimes be valid in the solution that we are given, in the problem that we're given. Okay, I want to add one more thing, and it will then lead into the non-degenerate constraint qualification. And that is that sometimes the tangency condition will be hard to find if there's a weird relationship between multiple constraints, and the way that you calculate the slope of those constraints is going to be problematic in comparison to each other. And that, combined with our corner solutions being problematic, are ways that our standard methodology of finding tangency will not work. And so what is inbuilt into the Lagrange theorem that will address all of these concerns is a investigation of the NDCQ. So NDCQ, non-degenerate constraint qualification. This is a way of checking with an algorithm the whole problem to see if there's any issues like this, or like strange constraints interacting with each other that will prevent us from finding tangency in our solutions. And we can focus all of our attention of these problems in checking the NDCQ, and it will mathematically allow us to identify points that are well behaved or not well behaved, and in doing so, flag any potential issues for us. So a lot of people find NDCQ kind of confusing because the process itself is an algorithm that you just have to learn how to do. And the way that it actually addresses all of the things that it does address is hard to understand. It's a bit abstract. But you don't need to understand the ins and outs as to why it works. Instead, you just need to know how to correctly check the NDCQ, and that in doing so, you are dealing with these problems. Okay, before I go into the mechanics of this algorithm, let me give you an analogy. So if you drive a car, or you know how to drive a car, or you can just imagine what it's like to drive a car. If you're on a highway, some place with multiple lanes, and you're trying to change the lane, then most of the looking that you do is going to be in your mirror. Your mirror will tell you what is behind you, and you can use it to see if there's space for you to change lane. And yeah, the bulk of the look is actually done by checking the mirror when you're in a car and you're trying to change lane. But the mirror is not enough to check, to then see that there's nothing going on in your mirror and therefore you're safe to change lane. It's not enough. You need to do another thing, which is shoulder checking. And that is after you've checked that things are clear in your mirror, you look over your shoulder and you see if there's any cars that are in the blind spot of your mirror. And that is equivalent to checking the NDCQ. The theorem that we're going to be looking at, the Lagrange theorem, has a blind spot, which is caused by things like this. And the investigation of the NDCQ is checking the blind spot if there are cars, so to speak, in it. And it's really good practice when you're solving these problems that you don't just rely on jumping straight to the conventional answer or the conventional solution approach, which is the Lagrange theorem, but instead you also check the blind spot of that theorem when you're using it. That is equivalent to trying to change lanes and only looking in your mirror and changing. Most of the time, nothing bad will happen because there's no car in the blind spot and you know enough information to go across and you'll be fine. But if you always change lanes without checking a blind spot, eventually there'll be a case where there is a car in that blind spot, and because you didn't check it, you're going to crash. And that is equivalent to solutions being in the unconventional places. Okay, hopefully this motivation can help get you through understanding the mechanics of checking the NDCQ. So let's have a look at that. Suppose our constraint set is given by this. And in this constraint set, there are multiple constraints, multiple h functions, and all of them are equal to some constant. And the set C is the set of all points that satisfy all of those conditions at the same time. The way that we investigate the NDCQ on this constraint set is we calculate the Jacobian matrix of this, which is just a matrix that has all of the partial derivatives of every single constraint. So if you had two constraints and two inputs, this would be a 2x2 matrix. Okay, and we call the Jacobian, we call dh of x the Jacobian, that's what this means. And for the NDCQ to be satisfied, it needs to be full rank. And if that's true, then that means that the constraint and grad vectors are linearly independent. And ignore this here. There's another video that I've made that will explain how to check if things are linearly independent. And yeah, that's what it means for the NDCQ to be satisfied, is for this to be full rank, which means the constraints are linearly independent with each other. Okay, practically we achieve this by evaluating all of the constraints and then systematically going through them to see if there are any issues. First, we check that individually none of the grad vectors are equal to 0, because if they were equal to the 0 vector, then the gradient vector isn't linearly dependent even on its own. So a grad vector of 0, a vector of 0, 0 is linearly dependent to itself, which is a problem. And then if you have multiple constraints, we check if they are linearly dependent or not with each other. And then we just keep going for all of the possible amounts of constraints. So if you have two constraints, then you check that neither of them are 0. And you also check that neither of them are just a scalar multiple of the other. Okay, and then you do this for all the combinations of constraints possible. Okay, putting this all together, that's the conclusion of the NDCQ there. We have our Lagrange theorem. Now, Lagrange theorem says this. If f, h are continuously differentiable on an open set, and a constraint set is given by this, where we've got h is equal to c, then if x star and y star is a local extremum of f being graphed on the domain of C, and the gradient vector is not 0, 0 for this one constraint here, then there exists a lambda star such that xy lambda is a critical point of the Lagrangian, which is the critical point of this function here. Okay, so to find a critical point of f of x subject to this constraint, we just find a critical point more generally to the Lagrange function. And now our constraint optimization problem has been converted into an unconstrained optimization problem, just this. And the critical points, when you calculate them, give us the grad vector of f is parallel to the grad vector of h, and that our constraint function is being satisfied. That's what the first order conditions of this Lagrange function give us. Okay, and then more generally, you can add constraints here, and in doing so, change the Lagrange function by just stacking them in the exact same way as this, but just all of them are then added with a minus lambda 2, h2 of xy minus c2, so on and so forth, which is what this here is talking about. Okay, and the process that we use to solve these types of questions is we, 1, check the NDCQ for any violations. 2, we construct the Lagrange function. 3, we list out the first order conditions. 4, we solve the system equations for critical points of Lagrangian. 5, we classify the critical points and NDCQ violations by using concave or convex programming, the extreme value theorem, or just being told in the context of the question that a solution exists. And then finally, 6, you answer the specific question based on what you've found above. So you interpret your answer, and in some exams or assignments, they ask for some specific thing that you want to make sure you're being intentional about answering at the end of your question. Okay, a fitting way to end this video is to go and actually look at a question specifically ourselves. So let's use the Lagrange theorem to answer this question here. Factory produces two types of machines in quantities x and y. Production costs are given by this, x squared plus y squared minus xy. Minimize the production costs of producing a total of 8 machines. Report the costs and exact number of each machine at the minimum. Okay, so we can convert that wall of text into this problem here. Minimize f of xy equal to this, subject to x plus y equal to 8. So that will give us a production of a total of 8 machines. And then here our cost is being minimized. Okay, so step 1, we check the NDCQ, checking the blind spot of our Lagrange theorem. Well, our gradient vector of our constraint function is just 1, 1. And that's not 0, 0 ever. And so with our only one constraint, there's no linear dependence issues with our constraints. Step 2, we construct our Lagrange function. So that is putting in our original objective function here, and then subtracting lambda, the constraint. So x plus y minus 8 gives us the Lagrange function here. All right, step 3, calculate the first order conditions. Well, there's 3 first order conditions here. Derivative with respect to x is 0, derivative with respect to y is 0, derivative with respect to lambda is 0. and that gives you this. So that's just simply differentiating this with respect to each of those variables. Okay, 4, solve the system of equations. Well, 1 implies that lambda is equal to 2x minus y. Plugging that into 2 for this, we get 2y minus x minus 2x minus y. Rearranging that down, we get x is equal to y. Plugging that into 3, x plus y is equal to 8. That means x is equal to 4 and y is equal to 4 as well. And then finally here, if x and y are both 4 and lambda is equal to 2x minus y, that means lambda is 4 as well. Therefore, together, we've got a critical point of the Lagrangian, which is 4, 4, 4. Notice that this is also positive in terms of x and y, because it would not make economic sense to produce a negative amount of inputs. So that's lucky. There are more intentional ways of making sure this is true, but incidentally it works, which is good. Okay, step 5, classification. So for our classification here, I just put it like this, we can show convex programming to work out this minimum. Remember, a function is convex when it has this shape, and that means the Hessian must follow this pattern here. So calculating the second order derivatives and putting it into this matrix demonstrates the pattern of the first leading principal minor being positive, and the second one, which is the determinant of the whole thing, being positive also. And together that means f is positive definite. So that means the Hessian of f is positive definite. And then f on C is thus convex. Easy. And our constraint set is a convex set, which is another thing that you need to check when you're doing convex programming, that the function is convex on the constraint set and that the constraint set is convex. And together that means we have a convex program, and so this is a global minimum. Easy. So our critical point that we found is the global minimum, and we have confirmed that through our classification. And then lastly, at the end, answer the specific question. So what did the question ask us to do? Report the cost and exact number of each machine at the minimum. So the minimum cost to produce 8 machines occurs when making 4 units of X, 4 units of Y, and at a dollar value of, plugging into objective function, $16. And that is the answer to our question. All right, I hope you found this video helpful at looking at constraint optimization with equality constraints as part of our problem. Thank you for watching, and I hope you found it helpful.